So we've got the difficult part out of the way with getting the computer system set up. Now I want to talk a little bit about the basics of math. We're going to go back to some of the very, very basic stuff in here. We build up kind of quickly. But I've found through the years that most of the problems students have with the more difficult math concepts like algebra and working with variables comes from not totally understanding what's going on with the very, very basics. So we're going to start with those very basics. Now, since this is, especially the first few days here, since this is all stuff that you have seen before, I try to approach it from a little bit different angle because you've already seen it done the standard way, and either you understood it and you don't need to see it that way again, or you didn't understand it and maybe seeing it a little bit differently will help. One of the things I try to do in here is I try to, whenever I can, I try to show you why things are done a certain way instead of just showing you how to do them. So one of the big concepts that very, very basic, but I found is actually very often misunderstood by students, is the concept of a number. What is a number? If I put a 6 up here, how many of you would tell me that that's a number? Show of hands. Most people would. Some of you know that there's a catch coming, so you're being skeptical. That is a numeral. All it shows is an amount. It's saying there's 6 items of some sort there, but it's not telling us what it is. And to truly be a number, it has to tell us what it is that we're counting. Is it 6 flowers? Or 6 cows? Or 6 whatever? Now it is a number. To truly be a number, it has to have those two parts. The amount and then a label of some sort telling us what it is that we have. So the two parts, the 6, which is the amount, I'm going to refer to as the count. That tells us how many. And the label, in this case the flowers, which tells us what it is, I'm going to refer to as the name. And to truly be a number, you must have both a count and a name. Now, don't go thinking that I'm one of those mean math teachers that's going to make you label everything or I'm going to mark it wrong. That's not my purpose here. I'm not going to be nitpicky like that. But having those two parts of the numbers and using both parts actually explains why our basic operations work the way they do. So I'm going to look at our two most basic math operations and how those parts of a number interact. So let's look at addition and multiplication. Now some of you might be wondering, well, addition and multiplication, where'd subtraction go? Where'd division go? Well, when you get into real mathematical theory, we've all been taught you have addition and you have subtraction. But technically, they're the same operation. When we look at negatives or integers, we're going to see that addition and subtraction are the same. Subtraction is just the reverse. In fact, the definition of subtraction is the reverse of addition. So anyway, any rules that apply for addition also apply for subtraction. The same goes for multiplication and division. They're the same operation, just one's going in forward and one's going in reverse. So any rules that apply to multiplication also apply to division. So let's take a look at something here. Let's say I have 6 inches plus 3 inches. What's my answer going to be? 9 inches. Probably not groundbreaking material quite yet. Huh? But let's take a look at what happened with our two parts, our count and our name. Our count, we had 6 and 3. Those were combined to make 9. So we combined our counts. We're adding here, so we combined them with addition. Let's look at what happened with the name. We have inches, and our result was inches. When we add numbers, we keep the same name. Now again, probably not horribly significant as of yet. But let's look at multiplication and see what happens there. If I take 6 inches times 3 inches. Just a little side note, by the way, this dot is the symbol for multiplication. We use that instead of the x, just so it doesn't get confused when we get to variables. I will still sometimes use the x just when it doesn't matter. But anyway, 6 inches times 3 inches would be 18 what? Careful, not inches, but inches squared. Usually if we're multiplying a length by another length or dimension by another dimension, we're looking at like a area or something like that. So that'd be square inches. So let's look at what happens with our count and our name again here. So here we have 6 and 3 combined to make 18. So we still combine the counts. This time we're multiplying, so we combine the counts with multiplication. If we look at the names now, we had inches, and it becomes inches squared or square inches. When we multiply, we also combine the names. And this is the big difference between addition and multiplication. When we add, we keep the same name. Now that implies that we must start with the same name. When we multiply, we're going to combine names, which means we don't necessarily have that restriction. For example, let's take 4 cows plus 7 boys. Do I get 11 cowboys? No, it doesn't work that way, does it? Let's reverse that. We've all been told 4 plus 7 equals 7 plus 4, right? So if I do 7 boys plus 4 cows, does that give me 11 boy cows? No. Anybody with a farm background in here? A couple of you? You can tell me that is a whole bunch of bull, right? A long way to go for a joke. I'm a math teacher, which means I'm required to have a really stupid sense of humor. But anyway, there's a point behind that. I cannot combine cows and boys with addition because when I add numbers, I need to keep the same name, which implies I have to start with the same name. I could add 6 inches and 3 inches because they both were inches. I cannot add cows and boys because they're not the same name. On a little more serious note, if I were trying to add 8 feet and 4 pounds, what do I get when I add those? Well, I get 8 feet and 4 pounds because they have different names. I cannot combine those with addition. But on the multiplication side of things, when I multiply, I'm going to combine the names, which means I don't have to start with the same names. 8 feet times 4 pounds, I am going to do 8 times 4 is 32. I combine the counts, but I also combine the names. Feet times pounds are foot-pounds, which is a unit of torque if you're dealing with mechanics, or a moment if you're dealing with structures and construction. That is legal because when we multiply, we combine the names. So when we multiply, we don't have to have the same name. Now you might be looking at that thinking, okay, kind of interesting, but probably not quite worth my $400 for the course right yet. But this, when you understand this relationship, it explains why we do things the way we do with all of our other forms of numbers. Let's take a look at everybody's favorite, fractions, like 3/7. Now I say that sarcastically, by the way, because I realize if I surveyed people on their way in the room, asking them what they hate most about math, 4 out of 5 people would say fractions. Most of the other one would say the teacher. So let's review. The top number of a fraction is called the numerator. Very good. And the bottom number is the Denominator, perfect. Little side note, by the way, if you ever see me pause in the middle of a word like that, I am a horrible speller. Usually it just means I got halfway through the word and I forgot how to spell it. I also know my handwriting sometimes leaves a lot to be desired. If anything ever appears up here and you can't read it, I assure you it was meant to be written in English. But don't be afraid to just ask me what something says or ask me to rewrite something if I get a little too sloppy. Chances are either butchered the spelling or my handwriting is just unrecognizable. I'm okay with that, so you won't offend me, trust me. But anyway, let's look at these labels here, numerator and denominator. To numerate, what does it mean to numerate? Well, every 10 years, our government sends out people to do the census where they numerate the population. What are they doing? They're counting. Denominator, what does it mean to denominate? Well, you have different denominations of money, different denominations of organizations. To denominate means to classify or to give a name. So the fraction 3/7, the numerator and denominator, are nothing more than a count in a name. Just like having 3 inches, or 3 cows, or 3 pounds. Here we have 3/7. Now when we add numbers, remember there's 2 things. One, we must have what? The same name. So what that means is if we're going to add fractions, I can add 3/7 to 2/7 because they have the same name. Back in about 3rd or 4th grade, when you first started working with fractions, that 3rd grade teacher pounded. When you add fractions, you must have common denominator, same name. That's not a special rule for fractions. Any number, when we add them, we must have the same name. We're just not used to seeing the label on most of our other numbers. The second thing then is, when we add them, you combine the counts, but then you keep the same name. So up here, to add fractions, you combine the counts. 3 plus 2 is 5. And we keep the same name, 7ths. Again, not a special rule for fractions. That's how we add any numbers. You combine the counts and keep the same name. If we look at, multiplication. If I had 3/7 times 2/7, that 3rd grade teacher probably told you just multiply straight across, right? 3 times 2 is 6. 7 times 7 is 49. Well, it's not just because that 3rd grade teacher said so. It's because that's how we multiply any number. You combine the counts and you also combine the names. So what if we had something like, 3/4 plus 1/5? If I go to add those, can I add them the way they're written? No, because they have different names. They have different denominators. Now, when we look at fractions in more details next week, we're going to look at how do you change the name? How do you change that denominator so that you can add or subtract them? But for now, all we need to know is we can't add those because they have different names. On the other side, however, when you multiply, we don't need the same name. Again, that 3rd grade teacher always said you don't have to have a common denominator to multiply. Again, that's nothing special for fractions. Any number, you do not need the same name to multiply. So we're going to combine the counts. 3 times 1 is 3. And then also combine the names. 4 times 5 is 20. So all those special rules that you learn for fractions are the same as the rules for whole numbers. They just look different because fractions look different. Let's take a look at another form of number, decimals. .21 would be one way of pronouncing that. What would be the formal way of pronouncing that? 21 cents would be one way of doing it. Yep. Or hundredths is another. There you go. Perfect. 21 hundredths. When you write it like that, now it's pretty obvious that there is a count, the 21, and a name, the hundredths. So let's say I go to combine 0.21 plus 0.3. I'm going to add those. Can I just go ahead and do this? Is that going to work? No, why not? Okay, somewhere around 3rd or 4th grade, your teacher told you when you add decimals, you must line up the decimal point, right? Well, that's not just because that third grade teacher said so. If we look at this, this is 21 hundredths. This is 3/10. They have different names. Fortunately, we can just do this. Put a 0 there, that's now 30 hundredths. So lining up that decimal point is nothing more than giving them the same name. So now we add those, 21 and 30 make 51. When we add decimals, what do we do with the decimal point? We just move it straight down, right? Because when we add numbers, we keep the same name. 21 hundredths and 30 hundredths better be 51 hundredths, keeping the same name. When we multiply, however, do I have to line up my decimal point? No, I don't. Because when we multiply, we do not need the same name. 21 times 3 is 63. Where's my decimal point going to go here? 3 places to the left. I got to add a 0 in there, put a 0 in there, and then put my decimal point. Why? Because you were taught, that 3rd grade teacher again taught you, you got to count 1, 2, 3. 3 decimal places in the problem. Then you go 1, 2, 3 decimal places in your answer, right? Look familiar? Well, again, why? Well, not just because your 3rd grade teacher said so. It's because when we look at this, this is 21 hundredths. This is 3/10. And when you multiply numbers, you combine the counts. 21 times 3 is 63, but you also combine the names. Hundredths times tenths is thousandths. I know it's a little sloppy, but you get the picture. So when you're counting those decimal places in the problem and putting that many decimal places in your answer, all you're doing is also combining the names. Again, it looks different because it's in decimal form and they look a little different. But it's the exact same rules, exact same processes for whole numbers. Let's do one more example. Let's do algebraic numbers. When we throw the x in there, that's when people start to get nervous. But again, this is just a single number with 2 parts. You have a count, the 4, and you have a name, the x. This is just like having 4 inches or 4 cows or 4 pounds or 4 sevenths. The difference is you know what an inch or a cow or a seventh is. You don't necessarily know what x is, but it really doesn't matter. If I take 4x plus 7x, I'm going to get, well, I combine the counts. 4 plus 7 is 11. And when we add numbers, we keep the same name, so that stays x. If I'm multiplying, however, 4x times 7x, I combine the counts. 4 times 7 is 28. But I also combine the names. Just like inches times inches became inches squared, x times x becomes x squared. So what if I have 5x plus 2y? What do I get? Well, when we add numbers, we must have the same name. Those have different names. So just like our 5 feet plus 2 pounds stayed 5 feet and 2 pounds, 5x plus 2y stays 5x plus 2y. We cannot combine those with addition. However, if we were going to multiply 5x times 2y, we're just going to combine the counts. 5 times 2 is 10. Then we're also going to combine the names. Just like feet times pounds became foot-pounds, x times y becomes xy. So again, it's the same rules as whole numbers. It just looks a little different because algebraic numbers look a little different. So you might be wondering, okay, this is nice and it works well with the simple numbers I've put out there. But how does this apply into our more advanced, larger operations? Well, the concept that ties it all together is the concept of place value. Place value is just a way of assigning a label or a name to numbers based on their location in a larger number. So now we're not going to talk about decimals right now, but we're going to use the decimal point. The decimal point's at the end of the number. And we go backwards to the left from there with our place values. This first place value is the ones. Then we have tens and hundreds. Good. Perfect. Those are actually our only 3 place values. They repeat over and over again. Ones, tens, hundreds. Ones, tens, hundreds. But they're in groups. This was our base group here. This is the thousands group. And this is the millions group. So when you name a place value, you name its place value and its group. So this would be just the tens place. This is the 10,000s place. This is the 10 millions place, and so on. Now I'm not going to dwell on those place values because you guys get the concept, and you can identify. If I give you a number 47,283. If I ask you what place value the 7 is, you can tell me it's in the 1000s or the thousands place, right? But those place values are important for a few reasons. The first one of the simplest reasons, is it defines what that number truly is. The 4728 that we're used to seeing, 47283, is really an abbreviation. That full number is 4 10,000s and 7 1,000s and 200s and 8 10s and 3 1s. That is the full form of that number, sometimes called the expanded form. In that form, it actually allows us to define the structure of numbers. You'll see here that every digit of that number has a count and the name. This is 7 1,000s. This is 8 10s, 2 hundreds. Every digit has a count and a name. And when you understand that, the way we do our operations makes more sense. The other big important thing for our place values is rounding. Let's say I give you the number 6,458 and I ask you to round to the nearest 1,000. Now we're going to come back to the shortcut that you all know in just a minute. But when I ask you to round the nearest 1,000, what is it really asking? What's it really mean? Well, a lot of things in math come back to a structure called a number line. And when we're asked to round, it is asking us to look at a number line. And if it's to the nearest thousand, it's saying, okay, let's assume that number line is only labeled to the nearest thousand. So this might be 5,000, 6,000, 7,000, 8,000, and so on. When it's saying to the nearest thousand, it's saying if I locate that number on the number line, which thousand is it physically closest to? Well, it is closest to the 6,000. So that rounds to 6,000. Now, you probably don't want to have to draw out a number line every time you round numbers. So the shortcut that we've all been taught is, if you're rounding to the nearest thousand, you identify the thousands digit. What digit's in the thousands place here? The 6. And then you look at the next digit, which in this case is the 4. Now, if you think about this, 5 would be right in the middle. And you got 1, 2, 3, 4. It's pretty obvious that all those are closer to the 6,000. Above the 5, you got 6, 7, 8, 9. Pretty obvious that all those are closest to the 7,000. If that next digit is a 5, is where we have some issues. Well, let's look at the 6,458. Let's say I asked it around to the nearest 100. So that's going to be 6,400, 6,500. The hundreds digit is the 4. The next digit's a 5. But 5 is right in the middle, isn't it? What have we been taught to do with those? Round them up, right? 6,500. We round this 4 up to a 5. Well, why do we do that? Well, because again, on the number line, this isn't just 50, it's 58. So technically it is slightly past the center. It is closer to the 6,500. Now, is there anybody in here that's going into like a mechanical design or applied engineering or composites or anything like that for their program? Okay. Or machining. I guess machining would take this. But if you're going into any of those types of fields, engineering, sometimes even architecture, there actually are some processes where if that's a 5 there's sometimes where you don't want to round all of them up. It's called the tolerance buildups, error buildups. I'm not going to discuss it here, but there are processes where sometimes you round some up and some down. If that's something you're curious about, let me know and I'll show it to you outside of class. For most applications, and business being the big one, if that next digit's a 5, you will always round up. I'm not going to spend any more time on rounding. If you have more questions, let me know and we'll go over it. But I do want to look at, since I got the number line up, let's look at some symbols. If I asked you to compare 8 and 12 using the symbols, remember those old symbols? Anybody tell me what this first one is? Less than. The middle one is equals. Yep, or equal to. And the last one? More than or greater than. You got it. Well, how do you remember where they are? Well, if I look at the 8 and the 12, it all comes to a number line again. If I look at 8 and 12 on the number line, what side is the 8 on? That side. What's that look like? That's where that less than symbol comes from. 8 is on this side of the 12. It's the arrow at the end of the number line. Okay, so let's now look at our operations with larger numbers rather than just single-digit numbers like we looked at before. If I have 254 plus 315, Now we discussed that these are just abbreviations of our numbers. 254 is really 200s. And 5 10s and 4 1s. 315 is really 300s and 110 and 5 1s. And remember, each digit is a count and a name. And when we add numbers, we can only combine things that have the same name. Back in first grade or so, or even kindergarten, you were taught when you add multiple digit numbers, you had to line up the columns, right? Well, that's because these 5 10s can only be combined with this 110. You can only combine digits that have the same name or the same place value. Once they're lined up, then we can just go ahead and add the columns. So I've got 200s and 300s make 500s. 5 10s and 110 make 6 10s. 4 1s and 5 1s make 9 1s. So that is 569. Now some of you might have been watching me do that and thinking, he did that backwards. What did I do different that you don't normally see? I started on the left and I worked my way to the right, didn't I? How would we normally add numbers? How are we taught to add numbers? Okay, start on the right and work our back to the left. Start with the smallest place value and work our way back to the larger ones. Why have we been taught to do that? Not just because the kindergarten teacher said so. In case you have to carry. Yeah. We might have 385 plus 476. We start on the right and work our way back to the left because we run into 5 plus 6 is 11. But we can't have two digits there, so we're going to keep this 1 and carry the 10. Carry that into the next column. 1 and 8 is 9, plus 7 is 16. So the same thing. We'll keep the 6 and we'll carry the 1 into the next column, next place value. 1 and 3 is 4, plus 4 is 8. Look more familiar that way? Yeah. Now again, you guys have the calculator, so I don't expect you to do a lot of long addition, but it is nice to be able to. I used to do a lot of construction engineering, and I'd show up on job sites, and my calculator would get thrown in the windshield of the truck, and it'd get warped in the heat and not work, or get dropped in the sand and some of the keys wouldn't work. It is good to be able to do that math by hand. By the way, this process of carrying is a relatively new process. And now by new, I mean a couple hundred years old. Before that process was invented, or became popular, I should say, one possible way that numbers would have been added would have looked like this. 3 and 4 make 7. 8 plus 7 is 15, drop the 1. 5 plus 6 is 11, drop the 1. 7 and 1 is 8, 5 and 1 is 6. Notice you get the same answer. The only reason I show you this, I'm not trying to change the way you add numbers, but I show you this to prove a point. I could actually show you 4 or 5 different ways to add 3-digit numbers, and they would all work correctly every time. In math, we've always been told that there's one right way to do things. There isn't. There's one right answer, but there's several different ways to get there. So you may have a different way of doing things. If you're not sure if it's going to work every time, let me know. I'd be happy to take a look at it and show you. Is this one? This last one? Oh, no. The core math, I don't want to get off on it, but the core math actually has some very good mathematical principles behind it. It's meant, I'll talk about, you'll see me doing calculations in front of the class, like some pretty long calculations I do very quickly, because math is about patterns. And once you start to see the patterns, the calculations are very simple. What core math is an attempt to do is teach students how to use patterns to do the math instead of going through cranking out calculations. The problem is it doesn't take the time to explain that it's a pattern. And you and I might look at the same problem and see a different pattern. And core math is forcing everybody to try to see the same pattern. For example, let's say you're going to do 57 minus 9. A lot of people would say, well, I'm just going to do 57 minus 10 is 47, so I'm going to add the 1 back to it to get 48. Others might do it differently. 57 plus 1 is 58, minus 10 is 40. Different shortcuts for subtracting 9. Well, in core math, they're showing you one of those. I could come up with 5 or 6 different ways of subtracting 9 that would make sense and would work, and is a quick way to do it. But and they're not doing a very good job of explaining. I can look at most of those and I can find what the pattern is that they're trying to get across, but it's just not. They needed to take more. They're trying to force it down. If you're teaching patterns, you got to really slow it down and take a lot more time with it. That's all I'll say about core math, but there is really valid math behind it. It's just not being presented in a very good way. Now, as I mentioned, you guys have the calculators, you're going to use them. I realize 3-digit addition, you're probably not going to do it out on paper if you don't have to. But I do ask that at the very least you look at this and say, okay, 385, that's about 400. 476, that's about 500. 4 plus 5 is 9, keeping the same names, it's hundreds. I'm expecting my answer to be around 900. So before you go punching that in the calculator, you have an idea of what your answer is going to be. So that if something like this happens, and you get your answer of 431, you know, hey, that doesn't seem quite right. What happened there? Yeah, when I tried to punch in 476, the 7 didn't register. I missed the 7 key. So you know that's not correct. Or it sometimes happens to me like this. There I accidentally hit an extra key. I know my 5,000 is not a reasonable answer there either. So before you start punching numbers in the calculator, if you can, try to have a reasonable estimate of what you expect that answer to be. Okay, next, let's look at subtraction. Now when I go to subtract, just like with addition, we could write these out in that full form or expanded form the book calls it. I'm going to assume at this point you guys get the picture that when you add or subtract, you can only combine things that have the same name. Therefore, you've got to line up the columns so that you're combining place values with the same place value. Now when we subtract, just like with addition, we're used to starting on the right and going back to the left. Why? In case you have to borrow. Just like here, 3 minus 7 can't be done. So we go to the 8, we borrow from the 8, that's now a 7, and this is now a 13. 13 minus 7 is 6. 7 minus 9 can't be done. So we borrow from the 4. That's now a 3, and this is now a 17. 17 minus 9 is 8, and 3 minus 2 is 1. And I realize that's the way that you guys are used to doing that, and that's how you're going to continue to do it. But I just want to show you that there's other ways to do it. One other way to do it, 4 minus 2 is 2. 8 minus 9 can't be done, so I'm going to borrow from the 2. That's a 1. This is now 18. 18 minus 9 is 9. 3 minus 7 can't be done. I'm going to borrow from the 9. That's an 8. This is a 13. 13 minus 7 is 6. I can go left to right. Works out exactly the same. A little bit more work, a little more paper. But again, I could show you 3 or 4 different ways to subtract numbers that'll work every time. I'm not going to because I don't want to confuse you. But just again, there's more than one way to do things. I realize again you're going to punch this in the calculator. So again, look at this and say, okay, 483 is about 500. 297 is about 300. 5 minus 3 is 2. I keep the same name of hundreds. I'm expecting an answer of around 200. Multiplication. I'm going to go down to 2 digits here. If I do 32 times 23, I am going to write this out in full form. So 3 tens plus 2 ones, and 2 tens, and 3 ones. When I multiply, do I need to have the same name? No. So what that means is this 3 tens here, not only can I combine it with the 2 tens, but I can also combine it with the 3 ones. In fact, every digit in the top number can be combined with every digit in the bottom number. So long multiplication is nothing more than an organized way of making sure we do that every digit in one number gets combined with every digit in the other number. And usually we start with the last digit of the bottom number, the 3 ones. And I'm going to combine it with the 2 ones. Now we combine counts, and we also combine the names. 2 times 3 is 6. 1s times 1s is 1s. Then I'm going to combine it with the 3 tens. 3 times 3 is 9. 1s times 10s is 10s. Now we move over to the next digit. What have we always been taught we have to do when we move over to that next digit? Well, down here we have to put in a 0 or move over a spot. Yep, perfect. So yeah, we put in that 0. Now, why do we put in the 0? Well, that'll become evident in this next step. 2 tens times the 2 ones. 2 times 2 is 4. 10s times 1s is 10s. We put in that 0 or we left a blank spot there because we needed to line up the 10s with the other 10s, putting together things with the same name. Then 2 tens times 3 tens. 2 times 3 is 6. 10s times 10s, hundreds. So now we just combine the stuff with the same name. 6 ones, 9 and 4 is 13, so 3 carry the 1, so 736. Now again, I realize you got a calculator, you're going to use it. So you're looking at, this is about 30, this is about 20. 3 times 2 is 6. We combine the names though, 10s times 10s is hundreds. 600. Now that's a little off from this, but remember both of these were rounded down. Both of these are less than what we started with. We're expecting an answer that's bigger than the 600. Okay, division. Long division is the one operation that's probably been changed the absolute most through the years, to the point where you don't even recognize what it is anymore. What you guys were taught as long division looks nothing like what real long division is. Before we get into that, let me do a little bit of preliminary here. When you first learn to multiply, let's say 5 times 3, before you memorized your multiplication tables and you knew that 5 times 3 was 15, how did you figure that out? You got it. 5 plus 5 plus 5. You added 3 5s. Repeated addition. Well, we said earlier that multiplication and division follow the same rules. One's forward and one's reverse. So it makes sense that if multiplication is repeated addition, subtraction or division is just repeated subtraction. 24 divided by 8 is asking, how many times can I subtract 8 from 24? I subtract it once, that's 16. I subtract it a second time, that gives me 8. Subtract it a third time, that gives me 0. 24 divided by 8 is 3, because I can subtract 8 from 24 3 times. That's where our remainder system comes from, by the way. If I have let's say I have 18 divided by 4. Well, 18 minus 4 is 14. That's once. Minus another 4 is 10. That's twice. Minus another 4 is 6. That's 3 times. Minus another 4 is 2. That's 4 times. 18 divided by 4, I can subtract the 4 4 times, and there's 2 left over. So 4 remainder 2. With that in mind, let's look at long division. Let's take something like 58,276 divided by 24. Now, we just said that division is repeated subtraction. This is asking how many times can I subtract 24 from 58,276. Well, I'm not about to start subtracting 24 from 58,276. We don't have that kind of time. But if I could subtract a bunch of 24s at once, it would make this go faster. How do I know how big of a bunch? I look at my place values. The number that I am dividing, what's the place value of this first digit? It's in the 10,000s place. So I'm going to try that. What is 10,000 times 24? That's 240,000. Can I subtract that from 58,000? No, I can't. So I move to the next place value, which is 1,000. 1,000 times 24 is 24,000. Can I subtract that? Yes, I can. In fact, I can subtract it twice. 24,000 times 2 is 48,000. So I'm subtracting 48,000. Leaves me with 10,276. Well, what I just did here was I subtracted 2 bundles of 1,000. In other words, I just subtracted 24 2,000 times. Does that make any sense? Right. What's that? Yeah. Oh, sure. I'll show you the... Oh, gotcha. I'll show you the normal way of doing it in just a minute. This is the very long version of division. So then our next place value would be 100. 100 times 24 is 2,400. I can, of course, I can subtract that from 10,000. I can do it 4 times. 2,400 times 4 is 9,600. So I'm going to subtract. I get 6, 7, and 6. 676. So again, I just subtracted 4 bundles of 100. That's 400. I just subtracted 24 400 times. So now, next place value is tens. 10 times 24 is 240. I can subtract that. Nope, not 3 times, only twice. So 240 times 2 is 480. Leaves me with 6, 9, 1. So 196. So again, I just subtracted 2 bundles of 10, which is 20. And now I'm down to the ones place. 1 times 24 is just 24. I can subtract that 8 times. 24 times 8 is 192. I'm left with 4 left over. So I just subtracted it 8 more times, and there's a remainder of 4. So 58,276 divided by 24 is 2,428 with a remainder of 4. Now you're probably looking at that thinking, that looks nothing like what I was taught. But it's actually exactly what you were taught. We were taught, you start with the 24 and you look at the first digit. Does 24 go into 5? No, so you leave it blank above the 5. That's what we did here. That we couldn't subtract that, so we just left it. So then you go to the next digit. Does 24 go into 58? Yeah, it goes in there twice. So you put the 2 above the 8 because that's the last digit we used. 2 times 24 is 48. You subtract to get 10. Now if you look here, that's exactly what we did down here. Only we left out all the zeros and we didn't bring down all the other digits. It's the same process. We've just left off a bunch of zeros and really, really shortened it. Now, I don't expect to change the way you do long division. I just wanted you to see where it comes from. The whole process of long division is just an organized way of subtracting large bundles of that number. So now, of course, you're taught you bring down the next digit of 2. 24 goes into 102 4 times. 2 is the last digit you use, so you put the 4 above it. 4 times 24 is 96. Leaves us with 6. Bring down the 7, and so on. You'll get the same answer. Now, once again, I realize that long division, I mean, it's the one operation I try not to do by hand if I can avoid it. So again, if you're doing the calculator, you can look at this and say, hey, that's about 60,000. This is about 20. 6 divided by 2 is 3. 10,000s divided by 10s is 1,000. So you're expecting an answer around 3,000. So when you get 2,428, at least you know you're in the right ballpark. Any questions? Okay. Probably a good time for our next break here, so let's do that. It's 10:54, so let's give you 6 minutes. We'll start up again at 11 o'clock.